Cool. So I'm Octopus. I am, among other things, I'm a research engineer here at Blockscience, and I have been reading lately about these multi-agent influence diagrams, and I'm really interested in how they connect to other frameworks that Blockscience currently uses, including generalized dynamical systems and both the current and the reference implementation of the cadCAD simulation engine. So to give you a bit of overview, we want to talk about each of these three things. There are three interconnected modeling frameworks that actually have a lot of compatibility and synergies. And I'd like to identify those and also to talk about ways that we might be able to use them at the process level to make sure that what we're doing in our modeling is coherent and efficient. I will go ahead and tell you, I don't tend to have very forceful opinions about things. So what I'm going to offer is explicitly options of things that might be considered. And then it's up to the organization and the consensus of what might be most useful to implement moving forward. So let's start with the multi-agent influence diagrams. As you might imagine, they're intended to capture the influence between multiple agents. They were introduced by Koller and Milch in 2003. And they're a diagram syntax that's useful for representing processes that can be understood as multi-stage games. They build on this prior work of things that already existed, including influence diagrams. And influence diagrams were also, or they were themselves a generalization of Bayesian networks. But both of these structures were typically looking at randomized probability distributions, and they were typically looking at things where there was just the actions of one agent to consider. So a MAID multi-agent influence diagram extends this in two ways. The first is we're now dealing with agents who are discrete rather than just one overall process. And we're also looking at decisions that they might make in response to different events. What I love about it is that it's a graph. I'm kind of a graph theorist by training, and there's so much that we can put into graphs, both in terms of visualization that makes it possible for us to understand what is going on, but also in terms of like hard computational analysis and actual structure that can be mined. I'm going to throw in a small disclaimer here, which is even in this one paper, there's far more concepts than could actually be elucidated in a series of talks. So we're going to be focusing most on what might be relevant to the processes that Blockscience currently uses and to the tools and concepts you're already familiar with. So one of the examples that was built by Koller and Milch in 2003 is Alice and Bob. Alice is considering building a patio behind her house, but unfortunately, Bob has a tree that blocks Alice's ocean view. And obviously, Alice would enjoy the patio a lot more if it had a clear view of the ocean, and Bob would enjoy his quality of life a lot more if he gets to keep the tree. So there's a conflict here. Alice may not be the most moral or empathetic person, and so her first decision is, should she poison the tree? We assume that she's not at likelihood of getting caught for our example here. That's going to lead to something that Bob can observe. He can tell whether or not the tree is sick. He cannot tell whether or not Alice poisoned the tree. All he can observe is that the tree may be sick. This is going to lead Bob to his decision, which is, should he call a tree doctor to try to help heal the tree? Now, Alice will know whether or not the tree doctor was called, but she will not know the ultimate outcome of it, whether or not it was possible to restore the tree to health. So she can see, she knows her own decision, and she knows the result of Bob's decision, which will lead her to her decision, which is whether or not she should go ahead and start building the patio on the likelihood that the tree might die. And we have a constraint here in terms of Alice's second decision, which is that she needs to start building the patio before the weather is too cold, and she does not yet know whether or not the tree's health has been restored. Each of these agents also has utilities, which are things that are values to them based on the results of their actions. So the first utility we can look at is Alice's effort to poison the tree. And this could be like effort in terms of she has to take a day off from work to do it when no one is watching, or just the moral weight on her conscience of the fact that she did this. And she's also ultimately going to have the final outcome of the quality of view that she has from the patio. Bob has two utilities as well that will ultimately influence how happy he is at the end of this scenario. He first has the cost to call the tree doctor, which we could express in a currency. And then he has the second utility, which is the value of the tree's presence to him, how much he cares about it in essence. And we can visualize these things using the MAID syntax. So the MAID syntax has a specific visual type for each of the things that occur in the scenario. We're using rectangles to represent decisions that agents need to make. We're also using circles or ovals to represent what may be called, or what are called, chance processes, which are randomized outcomes, which are still influenced by the agent's decisions, but that are going to follow a probabilistic process in terms of assigning what actually happens. And then diamonds are used to indicate the agent's different utilities. Now, here I color-coded the agent's utilities. It might also have been reasonable in retrospect to code their colors. The relationships between these different decisions, chance processes, and utilities are represented by two different types of arrows. There are solid arrows, which represent that there is a direct impact. For instance, the poison tree directly influences whether or not the tree becomes sick. And in the language of control theory and modeling, this might represent controllability of a variable. There is also dotted arrows, which represent observability or influence. In other words, whether or not we poison the tree doesn't directly determine or even directly influence whether or not the patio is built, but it is information that can be taken into account when the decision is made. So the tree being sick doesn't directly lead to the tree doctor being called, but it is information that the decision maker would utilize in the process of making that decision. And this is the graphical syntax for the multi-agent influence diagram. And it shows what each part of the model is in a clear and visually identifiable way. So I've talked for a few minutes now. Are there any questions or thoughts on anything that we've gotten up to this point, just in terms of the basic framework of what we're going to be looking at when we talk about MAIDs? I'll pause for about 30 to 45 seconds, and then if there's nothing in the chat or no break-ins, we'll move on.
Just a question about diagrammatic syntax. You've got dotted lines and dashed lines. Are they the same thing, or is the dashed line something different?
No, so you can think of the dashed lines as being like physical consequences, and the dotted lines are information flow. Does that make sense?
Yep. Thanks.
Yeah. It's like direct cause and effect versus just what I know when I need to get to when I need to act.
Mm-hmm.
So in this case, just to clarify, the Alice decision to build the patio, she knows that she poisoned the tree. She doesn't know whether it worked. That's a different thing, but she has information about her own actions, but doesn't necessarily have information about Bob's actions. I guess in this case, she could see them, so it's marked, but we wouldn't assume that by default.
Right. This would be, so in this specific example, it is assumed that she can like see the tree doctor's, van arriving at the house. But in general, we could delete that assumption and assume she doesn't know. And, she doesn't know whether the tree is actually sick. She would just know. Maybe Bob calls the tree doctor for a checkup every year. So it may actually be that doesn't encode as much information as we are assuming. Is that reasonable?
Yeah, it sounds great. If anybody else has questions about MAIDs, I'm not sure how many people are familiar with that. We're, I think, going to keep building on it or relating it to other stuff. So please feel free to ask clarifying questions.
Yeah. Like we said, productive use of time, and time is rarely spent productively if people are completely lost or completely bored. So the goal is to gradually be expanding knowledge. We'll say a bit here about the utility functions, which is it's difficult when there are multiple utility functions to come up with what the actual outcome of the process is. So a reasonable thing in modeling is to combine them in some way. For instance, we might want to add the cost of calling the tree doctor to the value of having the tree. The problem or the challenge is that this involves subjective choices. I know this is something Dr. Zargam has done a great job of highlighting in various contexts, that when we're building a model, often we have to make these assumptions. The cost of the tree doctor can be quantified exactly. The tree doctor charges some number of ETH for their services. But the value of the tree is not directly measured in ETH. It's a much more subjective thing that's internal to Bob. And so if we try to add something that's measured in ETH to something that's measured in a unitless constant, we're going to have issues. And this might require choices about how to translate and value these things. One thing that Dr. Shorish pointed out to me was that this is a common situation in economics. And so rather than just looking at the quantitative values of like assigning an ETH cost to the value of the tree and then adding that to the ETH cost of the doctor, you can still look at qualitative rankings that are likely to be consistent. So even without assigning the numbers, we know what Alice would most prefer. Alice's best outcome would be if the tree just dies. Without her having to do anything, the tree gets sick and dies, and then she can build her deck. The worst outcome would be that she goes to the effort of poisoning the tree and builds the deck, and the tree still survives and her view is ruined because this costs her the most and gives her the least desirable outcome. And then there are far more options that could be put here. I just put a sample of ranking the different considerations of which outcomes would be most desired to least desired. And in economics, I am told by people who are experts in the field that this is a common trade-off that one needs to make, and thinking about it both in terms of assigning quantitative utilities and subjective qualitative rankings are both ways to go about this that make sense and can be in some sense compatible. But the takeaway from this slide primarily is that we have to look at the overall agent utilities and think about how we will process them at the end to talk about a single coherent outcome. Okay, I'm not going to let y'all stay this quiet. So if you would give me a thumbs up or a go on in the chat or something so that I know this is understandable and clear, that would be great.
Thumbs up.
Thanks. I still have a bit of a college professor left that having student feedback, even though y'all are not college students, really helps.
Yeah, no worries. I was just going to add one thing that I really like the different ways of representing utilities, and also that we've been exploring some other trade spaces, ways of handling this with the fungibility paper that Jamshid and I wrote with Matt Stevenson. So if people are also kind of just interested in that question in general, there's some other work kind of poking around the subjectivity of valuation of things.
And there also the this calls out to me that there's a third player in this game with their own utility functions, and that's the modeler.
Mm,
Because it might be easy to try to come up with a quantitative cost estimate for what the tree is, but it may be more effective to try to come up with a qualitative estimate of what an ETH cost is and compare that. So that's a part of this too.
we can imagine the modeler that Alice's lawyer hires will be very different than the modeler that Bob's lawyer hires when all of this comes out about how much damage was actually done.
Competitive modeling.
Yeah,
I
excellent
think
point.
that's absolutely true. I mean, that ties into some of the discussions around computer-aided governance and just like what does it mean to use models in these kind of subjective circumstances. So, yeah, I actually think that's a pretty important point. And I'm sure we'll come back to it in other sessions.
And there's another player who should probably also be pointed out, which is there's kind of a mismatch if we have two agents that make decisions, and then we have these random processes. So it's common to take the perspective that there's another player named nature, and nature is actually making decisions. And this is a nice fit, especially for blockchain projects where maybe you have someone who's willing to spend some money just because they hate you, right? You can kind of tune nature's decision making from purely probabilistic to then targeted along specific paths to probe for weaknesses. So thinking of nature as a player that makes decisions can be another useful perspective that's also well established in economics. I don't recall at the moment who that should be attributed to, but I'm happy if anyone does know.
It's Harsanyi.
Sorry, can you spell that?
Yeah, Harsany.
That's a perspective.
YI.
I
Okay. I think his first name is Reinhard. I'll check it out. No, that's maybe Reinhard Sultan. I'll check it in. Harsanyi. John Harsanyi.
Thank you so much. Like I said, I'm not an economist, so I really appreciate people who are, and any other discipline that I'm lacking making these contributions. So that perspective can be very helpful in terms of putting everyone on equal footing, especially when we come back to the structure of this, that having nature as a player identifies and elucidates some structural considerations. Okay, continuing, there's an alternative, which Dr. Zargham has contributed and had already established before I began this, of different ways you can look at this. So another way to do this would be to highlight what the decisions of the agents are and what the utilities of the agents are by color coding them and by identifying them into things that might be thought of as subsystems, I think would be a reasonable categorization. The rest of the syntactic diagramming is still the same. Rectangles, it's just in rectangles, ovals, and diamonds. It's just that now we have two additional pieces of data. One is more clear identification visually of who the agents are. And also here we have types corresponding to what types of variables we would be looking at, which is useful when we actually build this into a model. So formally, we could identify like an actual mathematical definition of a MAID, which is that a MAID consists of a set A of agents. In this case, we'd have Alice and Bob. For each agent in the set, we have a set of decision variables that belongs to that agent. And so the common notation when you have this type of setup is to use a subscript to indicate who this belongs to. So for instance, we would have D sub Alice and D sub Bob in this example. We have a set of chance variables whose values are set by nature. And then we also have a set of utility variables for each agent. And this is communicating the same information just in a more mathematically formal way. Where the structure that we just saw comes in is you can represent it as a directed labeled graph in the sense of a graph from graph theory, where the nodes are decisions, processes, or utilities. And the edges come in two types. They're labeled to either indicate direct influence or information flow, as we talked about a moment ago. Now, I think the value in notation and formality here is that it opens up the toolkit that already exists surrounding what we have in the background. So I'd like to point out some ways that I see this happening. When we look at this as a labeled directed graph, it means that we can compare models on the level of graphs, which means that, for instance, it might be possible to keep a database of different graphs that have been used for different types of models. And there's a notion of when two graphs are fundamentally structurally the same called isomorphism. So if you were in the process of building a model for a new situation and you represented it as a MAID, and the organization already had a database of prior MAID representations, it would be very feasible to search the database to see if there were any similar models that you could look at as a starting point. This isn't inherent to like the formal mathematics of it, but it is an organizational process type thing that imposing the structure would ultimately potentially result in greater efficiency. And in general, graphs just have a lot of structure that can be explored. For instance, we can look at ultimately when the model grows very large, what are the chains of influence that exist within the model, either from our assumptions in building it or from processes that we'll discuss later, which can build models from observed data. I was really excited to see this representation because by grouping the vertices here with more than just edges, now we're in the world of hypergraphs. Hypergraphs are actually what I published about the most in terms of academic journals. And hypergraphs are beautiful. They have more structure than graphs because you can do things like clearly indicate within a hyper edge other types of relationships. And so in addition to the graph structure and the types of information processing that might make available in its own starting, giving it a hypergraph structure actually enables more insight through looking at it and asking questions like, how similar are these two models just at the structural level of hypergraphs? Hypergraphs, for instance, are often used in modeling something like gene regulatory networks, where there are lots of complex interactions between things. And then the representation as hypergraphs is one thing that makes it possible to easily identify when two models of that type are similar. I'll stop here for just a moment because we're about to move on to a different part. What could be added so that the next session we'll talk about more structure that can be added to this to actually turn it into a model, because at the moment it's not a computable model. There is nothing that tells us what happens or why it happens within this structure. But what we can add next are decision rules that take the relevant information and turn the value into a variable. We can also talk about strategies, which are different assignments of decision rules. So we could have like a gentle Alice who never poisons the tree. We could have a ruthless Alice who will always poison the tree. We could have different ways of assigning strategies to Alice or Bob. And then this information, when it is added to a MAIDs, makes it possible to do more analytic exploration of the games. For instance, there's an algorithm for solving for Nash equilibria. Once this information has been added, we can solve for Nash equilibria of the underlying game, which enables us to have some insight into the game before we move on to different types of modeling that we might want to do. It could actually help us look at what are the places that our computational models are likely to end up, so that when we run simulations, we are using those as a framework for understanding where the simulations might need to go. For instance, potentially saving computational cycles in the setup.
I would also just add that this kind of representation, especially if you have an intuition for it after working with it for a while, can help you tune your model kind of back to the modeler as player, so as to be able to ask and answer questions. So I don't know if we have Danilo today, but he's very good at this skill, which is sort of helping figure out the shape of the model, which will be scientifically useful for answering relevant questions. Since we are almost always building models of the world, kind of in a map territory kind of way, we need to tune our maps to actually help us through the territory. And this sort of more intuition that you have from experience modeling, the more likely you can design your model in such a way that it supports answering questions, not just telling stories. And I think this is something we encounter frequently with clients, is they have a story in mind, not always a scientific question to evaluate, but from the perspective of design, at least, it can be really important to surface non-trivial, like, we don't know what will happens, and building models that will help us say, oh, well, under these circumstances, we might expect this, and under those other circumstances, we might expect that. And in the case of Alice and Bob, it might be as simple as, you know, what are the ranges of the, I don't know, costs of the tree doctor for which we would generally expect X outcome versus Y. And it can vary pretty widely, but the emphasis I'm trying to place here is that having practice and experience with modeling as a subjective act ties into both the implementability of the simulation, but also what kinds of questions you can actually address through simulation, as well as mathematically. In fact, I'm a big fan of using formal representations to unlock analytic assertions. But there's always going to be limits to what you can do analytically, especially with these very open loop problems, you know, that you simulate forward. Anyway, I'll stop talking now, but I just, since you were talking about implementability simulation wise, I think it's really worth noting. We do a lot of that subjective modeling step. Yeah.
Cool. I've tried to sticky note what you said, although unfortunately got part of it cut off, but I wanted to capture it here. Hopefully it's accurate enough.
Yeah, and obviously I say stuff like that all the time, so I think people are used to it.
We have a question from the chat. Is there a potential to query by decision rule? And the answer is yes. One of the things I want to talk about, probably not in this session, but the next session, is how you could look at the strategy as a parameter in the cadCAD model by making just a few small adjustments in how the initial agents are set up, so that later when you look at it, you can search for what the rule is. Now, in terms of like a database, I'm not a database expert, but it seems like with a little bit of additional, say, typing information of what type, like how the rule was constructed, you know, if you enforce a type, you can compare those. Now, if you have a decision tree model, it is actually the same as like a piecewise cubic model, and you would have to enforce some type of formatting of how to determine if they were the same, which would be a challenge in the record keeping. But in theory, you can structure decision rules in such a way that they're easy to search, as long as there's some type of consistent format. Does that make sense? Sounds like you need a flexible structure for inferring type of pattern data from unstructured data. Very much so. Probably the easiest thing to do would be to demand a common format, which is always risky. And if you don't do that, then the problem of comparing whether or not two decision rules are really the same is probably going to be very difficult.
I think this is worth kind of throwing into the bucket of our knowledge organization infrastructure overall. So if you had a particular decision rule or policy and a particular, that's like a mathematical representation, then you might have a computational or an implementation of that, potentially in a particular language. And you might also have empirical data about the historical performance or input-output data about that operation. And those are all different representations of the same thing. So you could do comparisons at the level of, hey, the checksums of the code are the same. You could do comparisons at the level of, is this code an implementation of this math? You could do comparisons at the level of, are these two programs generating the same input-output signatures when their data is analyzed? And those are all distinct modes of comparison. And I think insofar as we've been working on kind of these human assertions of similarity or even machine assertions of similarity in the, actually that's the hypergraph thing I referred to earlier that Orion and David and team have been working on, involves just being able to make claims about the extent to which two things are the same or not. And so I would argue that, yeah, this is kind of a big rabbit hole, but it's also a pretty interesting rabbit hole from an engineering standpoint, because we really do want to be able to say things like, you know, this mathematical expression is this code implementation, generates this behavior, or has, you know, historically generated this data. And even though those are sort of references to different things, abstractly, they're references to the same thing, and being able to create or at least maintain statements about the sameness is part of what the Neo4j based sort of hypergraph model that Orion, Luke, and others are working on aims to do. So I don't think we have Orion here. If we did, I think he could chime in a bit more, but might be an interesting discussion at some point in the future.
You know, the only thing I can add to that is that there's a very big difference between the problem, the difficulty of determining sameness and the difficulty of determining likeness. And that's a big area of research in the KLI space.
I feel like sameness is just conditional likeness. It's like something, you have an equivalence. Maybe this is too much of a math tangent, but you have to define an equivalence relation in order to get sameness. And an equivalence relation is like these specific kinds of likeness, but also I don't care about the other ones, as a way of getting to something formally assertable, as opposed to something that's a little bit more, oh yeah, they're kind of the same.
Yeah, that's the lossy way of doing it, but then it's the deciding what you can throw out and still have a well-stated problem is
Sounds like modeling.
Yep.
All right, I think we should give Octopus back the floor. Never mind, we have a small tech.
Can you hear me okay now? So I'm shifting.
Andrew, could I see this slide one more time?
Yes, I'm going backwards to the hypergraph slide. And to be clear, I don't deserve credit for the graphic.
Trans processes that. So this can be simulated, but it could also, yeah, this could be simulated fully, but also partially and deployed in a stream.
Yes, it could be encoded in it could be encoded in lots of ways. I think that would be a valid one.
I think if I saw correctly that the next bit connects into GDS, which in my opinion opens up this to thinking about implementations even more, simply because you can separate the admissible actions on the part of the actors from the system, as it were, that implements it, whether natural, physical, computational, or otherwise. So if I'm getting that correctly, then maybe we should move into that section.
That sounds good. And we'll return to MAIDs. There'll be multiple sessions in the future. So what we'll talk about next is generalized dynamical systems, GDSs. We're going to build a GDS representation of this system step by step. And the hard part in terms of one of the modeling decisions to make is which variables need to be tracked and how they are tracked. We could start, for instance, with just the 3 Boolean variables that will be updated at each stage. We could look at tree sick, tree dead, and deck built as all initially being set to 0 because none of these conditions are true in the system. And we could look at that as either like a dictionary type structure where the key is included, or just as the vector 0, 0, 0, and we kind of implicitly know the order in which the state variables are input. Or we could keep track of more than that because the agents may need a little bit more than that to determine their own decisions. And then the question is kind of like which of these are tracked in the global state and which of these are tracked in the agent state, and not to get too deep in that rabbit hole. Probably we need at least 5 variables for whether the tree was poisoned, whether the tree was sick, whether the doctor was called, whether the tree was dead, and whether the deck was built. And we might, oh, go ahead.
I have a question. So interestingly, my intuition would have been to go with a finite state machine, which is slightly different as opposed to a bunch of bits, because you could have the state where, the tree can be not poisoned, not sick. You have the doctor called, the tree dead. Like this collection of things has a kind of, let's call it like a non-trivial collection of combined states that it could be in. And so here we have rather naturally kind of a vector of Booleans, which does make sense. But given how much you like graphs, I was maybe just highlighting surprise at the choice of the vector over like a state machine representation of the system state, like a finite state machine representation.
Yeah, that's actually going to be in a second when we.
Okay, sorry.
No, that's fine
Please
because
go ahead.
there are all these different ways you could do it. So
You're good. You're probably better off starting with the thing most people would have started with and then continuing. You know what, I'm going to stop interrupting you.
no, you're good. Because here there would be like there are a lot of unreachable states is the problem. Like we basically have 8 bits, or we have 3 bits for 8 different possibilities on the tree's health. And that's really overkill because there aren't that many different possibilities. Like the tree cannot be dead without first being sick in our representation. So we're including information that may or may not be helpful. I was actually thinking about this from a machine learning perspective, because what we would ultimately do if we were reverse engineering, say with a system dynamics type model, or even trying to infer, if we didn't have this model and instead we had the data and we were working backwards towards a Bayesian network and machine learning, when we create the dummy variables in pandas, we end up with this from that we would need to work backwards from the string representation. That's why I thought to start with this one. But you bring up an excellent point, obviously, that there are multiple ways you can think about this. And you could, instead of keeping the bitwise representation where there's a Boolean for each possible state that the tree is currently in, you could track according to progression of potential states and something that might look more like a finite state automaton or a Markov chain for the individual tree. And that's more an art than a science, I would say, that if you start with this representation and then later you want to do machine learning on it, you will end up translating the tree variables back to bits. And then if you start with the bit representation, you'll probably translate to strings at some point to make it comprehensible to the client or other members of the audience. So there are multiple representations, and I think the key thing is they all have compatible information that can be translated between them.
Yeah, I actually think it's worth pinning this in your mind as like coordinate system transformations, because that also equips you with questions of whether they're lossy, or whether they're like, for lack of a better term, whether or not a particular coordinate system can get back into the previous one, or Yeah, I don't want to ramble about this too much, but what I realized as you were talking through it is that if you're really interested in things like reachability analysis, you don't want to presume that certain states are unreachable and code in, say, the state machine the fact that there are only these states. You might prefer the larger, more blown out system model and then demonstrate that that certain states are unreachable. And again, it might depend on what you're using the model to do, but the more you impose in terms of this restricted state space, the less you can analyze about that state space. So you're, as always, doing a kind of trade-off between simplifying your model by imposing more and opening your model up and looking for ways to make hypotheses or analyze sensitivity, because there are obviously conditions under which you could modify the MAID or the game such that states that were otherwise unreachable might become reachable.
I would like to add two things before returning to the main thrust based on what you said. My actual bias towards Boolean variables is this approach from Reinhard Laubenbacher's modeling school that translates from a variety of different models to things that can actually be algebraically solved based on representing the transition rules as polynomials over a finite field. And this is it's a little bit awkward with continuous data, but for their purpose, which is primarily gene regulatory networks, it works really well. And then you can actually do things like solve for the limit cycles in your model analytically without needing simulation, because you can solve for the polynomial solutions, which is often very efficient. That's an advantage of this representation. The disadvantage is it's huge. It's needlessly large compared to the more compact representation. It's double in size already. And for something where simulation is absolutely unavoidable, doubling in size is a big deal. And then nothing is worse than getting to the end and saying, man, I wish I had included that in the simulation. And you need that variable and you don't have it and you have to rerun it. Or
Yeah, and also I think just to push on it, there are versions of this that show up in a bunch of other places. So like minimal realizations, if you're doing system identification, it can show up in sort of the reduced form coordinate systems, which popped up in like the work Jamshid and I were doing on representing the homicidal chauffeur problem. There's like a kind of bigger representation and there's kind of a smaller representation of it that's more succinct. And I think this is the kind of modeling decision that people should get comfortable with, that like making trade-offs in terms of how much we blow things out versus how much we pin them down, with this sort of a continuum from the most massively blown out to the most constrained, and making choices about where to put the complexity ends up being a big part of our job. So I actually think this is a good place to be discussing, and maybe we'll come back to it in other presentations when we're dealing with similar topics.
sure, I'll be happy to investigate that. So modeling can be so artistic and it's hard sometimes to know. It's hard to strike the balance between like process and the fact that creativity is really unavoidable in good modeling. We might also need to include time, especially if we're looking at a model where this game is played repeatedly, or to keep track of the fact that maybe we veered into an unacceptable state where someone tries to poison the tree after it's already dead, or someone tries to build the deck before they poison the tree. And if we want to enforce a notion that's coherent with the stages that we assumed at the beginning, then keeping track of time can be useful for that. Although it might not be strictly necessary in the MAID's perspective, it's extremely useful when we move towards thinking of this in dynamics terms. So in a generalized dynamical system, the input space is the set whose items set the values of state variables or can potentially change the values of state variables. For instance, here in this example of translating this MAIDs to a generalized dynamical system, I have identified 10 things that could go in as a signal to change one of the state variables, which would be they're grouped according to the decisions. poison the tree or don't poison the tree, call the doctor or don't call the doctor, build the deck or don't build the deck, the tree gets sick or it doesn't, and the tree dies or it doesn't. So at each state of a time step in the model, this is something that could be input on the GDS level. And this would be the space of all possible inputs to the model. And I've partitioned them here in a way that the GDS structure doesn't natively have, but into the agent decisions in the top 60%, and then the random change processes in the bottom 40%. And so the way this works is similar to other types of discrete time modeling, where we take our current state, which I'm representing with X. Probably this should really be X sub 0 or X of 0 to indicate the dependence on time. And then we take the input, which I'm calling U. And here we have the initial state where nothing has happened. And the input is the poisoning of the tree. And then we update that to reflect the fact that the tree has now been poisoned. And this is how the mapping of current states and current inputs to the new state in the system will work. I am intentionally at this point minimizing the notation. There's some really nice notation, but I want to emphasize maximum accessibilities here. There's a comment from Dr. Sargam. I think this is closer to discrete event than discrete time, that those can be bound to each other with clocks and rules about how time passes. Yes. I think I implicitly made the assumption, which I failed to capture, that each stage is the same length of time. But that doesn't work for a lot of systems, and it's important to point that out.
Sean's also done a good job in the math spec library, the MSML, including literally a time policy. And basically, you could have anything from, hey, it's always a fixed period of time, to like stochastic processes that determine the time between events, to just like, just recognizing that there's by default, these are all discrete event systems, the ones that we're working with, because we're describing everything in terms of events, and that we've actually left a lot of flexibility around how we model time, in a large part because the right way to model time will depend on the thing we're modeling, and we don't want to be overly imposing about it, because it could be a period of time, it could be a block on a blockchain, it could be a lot of things. And actually, what I like about some of the notation that you're using here is that it makes sense, even if we haven't said whether it's fixed periods of time or waiting times between events, etc. That will matter, but it's less sensitive to it than it could be.
Actually, can I add on to that? Because we were talking about this actually on a recent meeting, but the idea of like often, so cadCAD models that we do right now, it's often like we think about it in, like that discrete time, like, maybe it's one day or something, but there is, this other paradigm of modeling where it's kind of event queue based, and you can actually have this event queue that says what's going to happen in the future, maybe, but things can get inserted, things can get shifted around, etc. And you can even think about it more like an event comes in and you're like, okay, the time has now progressed by this much, because it's like the first event and the earliest event in the queue determines what the time step increment is. And I think that's an interesting kind of way of modeling that we don't always do. We tend to usually, for a lot of the client projects at least, go with that like one day at a time. But there is always this other option of like actually having it, be like an event queue that determines how time progresses in the system. And you can even have like, I've done this with a lot of MSL ones where it's like, you could have a variable into a block that says delta time, and maybe you're doing like a return distribution for the exogenous signals, and you use, delta time to determine the actual variance in the random price distribution movements. So I think it's really cool and, something interesting.
So maybe it would be more accurate to call this event number. Add another thing that's like event number, how many events have been processed. And then time is another variable that gets, and there may be different notions of time, like with different systems, like
I
two
think
different
that's
blocks.
great.
Yeah.
But specifically because the events end up actually being partially ordered. The notation that we've been discussing includes things that can effectively happen in parallel or actually can be thought of as occurring in an unordered way, right? DAGs are partial orderings, not strict orderings. So there can be circumstances where, well, the computational implementation requires an ordering, the actual mathematical object, the thing that we're describing and analyzing, and even the real implementation where humans potentially are making decisions in parallel without the ability to observe things that are other things that are happening in parallel, all of that boils back to the discrete event model has a certain amount of partial orderingness to it, and that it's only when we broadcast it onto a clock that we actually get the strict ordering. And that's not even necessarily real. Like sometimes when you're broadcasting things on clocks, that's just so that you can, make visualizations. It might even be more useful sometimes to focus on the partial orderings because you get a better sense of what has to happen with essentially in parallel or without awareness of other things. And I think especially for systems that are multi-agent or physically distributed, it ends up being, I guess, or also computationally distributed, it becomes kind of important to be able to handle situations where you don't actually know whether things are or they're not orderable even. Like they could be happening on different computational substrates, and I'm running off on a rabbit hole now, but I think this is right to think about it as event queues, but just remember that as we think about systems that might even interact with outside systems. So imagine we were using a cadCAD model and running transactions on a test net that has its own state machine, literally, then there might be actually things happening like, I don't know, one cadCAD model controlling one agent, like one cadCAD model controlling another agent operating on a third substrate like a testnet could easily result in situations where there's a very real parallelization that doesn't have an absolute reconciliation. And again, I'm just sort of like trying to make it concrete, but this idea of these as discrete events and partial orderings, I think is a good rabbit hole. We can pin it as a rabbit hole, but it's something people should have on their mind because it ends up being relevant in projects.
What's
I'd
handling
like-
the reconciliation between models, though? If there are a group of models being controlled, right, and there's a transition between models, and there's another group using another model, how does the reconciliation happen in terms of information flow between those agents?
And I think that's something that has to be specified in the model, most likely. Also, there may be different regimes, like what Dr. Zargan was saying earlier, brought to mind the notion of a phase transition between different rule spaces that might have reduced different outcomes. And you could have the rule set that is currently in place be flexible, be dynamic itself, and also be something that's explicitly tracked in the state space rather than a parameter that's external to the model. And Dr. Sargon, what you said, I think from a game perspective, there are, for instance, MEV is an instance where timing and the order in which events are processed and the fact that it's different than the order in which events arrive is crucial to the actual game that's being played. And there are lots of games where timing is a strategy, or stalling, for instance, stalling your decision to minimize the information available to another one. Like we're working with a pretty rigid structure here that makes a lot of assumptions.
But I guess part of what I was getting at is that like within GDS, at least we have it's relatively underspecified. So you can actually start specifying systems. Again, you add structure, but you can add structure related to what I'm going to call distributedness. And this came up on a project work session I was doing with Christine earlier today. We were talking about the difference between the state of like a publishing network associated with the actual uploading documents, having identities, and a process that is effectively describing the state of a peer-to-peer network, potentially coexisting with a set of smart contracts that have their own state, kind of maybe local to a blockchain network. But then you have information where potentially one will affect the other or vice versa. But so from a modeling standpoint, we might write a system model that describes both of those processes. But from an implementation standpoint, they exist in what is effectively different again, it's not physically distributed. I guess maybe you could say it is, but like I think of it like a physically distributed system where the state of a subsystem resides in that subsystem. The state of another subsystem resides in that other subsystem. So both your kind of abstraction mathematical models and your eventual kind of data sciencey models sort of pull those things together into an abstraction that imagines both of them, but still deals with the fact that those systems are not in fact on the same clock, so to speak. They actually live in their own little universes, and you're assembling a representation of the system, the whole system, that includes, oh, I might get some data from here and some data from there, and I might need a means of reconciling them. And so part of what you're actually doing is constructing mathematical or computational definitions that allow you to take things that are not actually natively joinable and kind of roll them up and join them so that you can look at how the whole system is evolving. But that just comes back to the subjectivity of modeling, because to some extent, there may be many ways to do that, but some might be more useful than others with regards to, say, steering or designing that system.
Cool. I look forward to exploring this rabbit hole more. I want to move on now to, because we have identified some of the pieces here, and I do want to tie this back together both to GDSs and to cadCAD modeling, what MAIDs can tell us. So it is the case that in a GDS we have this admissible input space, which can depend on the current state of the system. For instance, if the tree is already sick at some point, we cannot then give the input that the tree doesn't get sick, because that would be incompatible as an input. So in the process of updating, we filter down from the space of all inputs to the space of inputs that are just admissible or coherent within the decisions that have already been made and the information that has already been established. And so the states are updated according to actually multiple pieces. We have an admissible input map, which, given the current state, determines what actually could be an input, what is an admissible input. And then the input map takes those pre-filtered possible admissible inputs and determines the input that will actually be input into the system. And this could be based on anything that can select an element from a set, which could be like a logical rule, like a mathematical or a computational function. It could be randomness from some probability distribution or any combination, as long as at the end it produces an input from the admissible input space that's already been pre-filtered. And then finally, there's the state update, which takes the state that's been selected or the state that already existed and the input that's been selected from steps 1 and 2 and produces the new state that the system will be in at the end of this. And these are like the big picture idea of how a GDS works. And the more of it is just about giving more formalism, I would say. And hopefully that's compatible with what both the originators and the current proponents would see it. So we have our MAID variables, and then we have our GDS input space, and there's a pretty clear correspondence between the two. That anywhere we had a variable in our MAID, we could represent that as an input, where this input will be specifically updating this state variable that was defined that would probably still be a state variable in the GDS depending on our choices of representation. And this is basically how we think about the inputs and how they are used in updating the state variables. So the goal here is to emphasize this correspondence of translation between how having a MAID already set up might make the structure of a GDS for a system more visible by highlighting what the inputs are and how those change the values of state variables. Next, I'm going to move on to cadCAD. Do you want to check in case there are any comments or questions about the speed run through the GDS part, which can be expanded more, and the literature on that is available that does expand it more, and we can return to that in future sessions as well. So one major use of MAIDs is that they can serve as a translation step for creating a GDS. And then there's also a natural correspondence between MAIDs, GDSs, and cadCAD models. There are people in this room who know much more about cadCAD than I do, but essentially a cadCAD model has 5 primary parts. In the Python representation, it has a state, which is a dictionary. Each key in the dictionary is a variable in the state space, and then the value for that key is the value of that variable at a given moment in the evolution of the system. Then there are the parameters. Parameters are things that are set outside of a simulation run, but that influence the evolution of the system. The basic example I use with complete beginners is that slope and y-intercept are the parameters of a line, y and x are the state variables. Then you have policy functions, which provide the logic that determines which decisions are made to determine the inputs of the GDS. And these inputs will update the state variables like we just saw and discussed. There are the state update functions that perform the actual state variable updates using information that is passed through from the policy functions. And then policy functions and state update functions are wired together into partial state update blocks that ultimately result in the system updates. This is not the right context to do a very deep dive on cadCAD because there's already a lot of existing information. And again, there are lots of people who know it and use it better than I do, but I wanted to include a definition because we're going to be talking about how these things might map to representations within the GDS and within the MAID. And just to illustrate that, you have this nested set of dictionaries where you have the label on the dictionary, and this dictionary consists of policies and variables that perform state updates. So we have this structure that illustrates what we were just describing. In terms of thinking about translating from a GDS to cadCAD, you can think of the policy functions as performing the admissible input and input steps, so that this determines what actually gets fed into. This is the U in the notation that we were using earlier. The policies are actually what determine the U that goes into the state update variables. And then the rule for updating based on the prior state variable and the current input determined by the policies occurs within these state update functions, which is a separate variable, separate dictionary. So from a modeling perspective, if we choose to use the MAIDs representation as the jumping off point for our GDS, for our cadCAD model, you can already see a specific structure that this would enforce. You can see, for instance, which decisions will update which variables and the order in which those variables will need to occur. So that in theory, it would be possible for a well-trained non-programmer to outline the cadCAD structure from the MAID without needing to be able to implement the component parts in the code themselves, which might be useful as an efficiency step or a structure step.
We might even be able to, and this is a appeal to Orion, who's all still not here. We've discussed using the CAD canvases and some of the TL draw work that he's been doing to go directly from drawings, literally like the ones that you have here, and binding the visual logics to something like code structure. So although it wouldn't give you all the code, could potentially give you a process for generating the outline of a model that matches a MAID just from the drawing. And so I think I'm going to pin this because I know we're getting low on time, but it's worth noting just for the team that this is a use case that we have in mind, and that if you're interested in it, the person who's most likely to implement at least a prototype of it is Orion.
This goes to the classic software axiom, code to the interface, not the specific implementation. A structure like this can give the interface that you are then coding to, so that you know exactly what needs to be written, and that work can be divided up and transferred between different team members. So I can work on the poison tree function while you work on the tree doctor function, while someone else works on the build patio function. And it's clearly structured and divided up what needs to happen. And then our task is to determine the logic.
How do you, in this system, how do I know what the purpose of the tree doctor is? Like, how do I know that? If a tree doctor comes in here, how do I know why it's here?
I don't know that that's discernible from the pure structural representation that we have here. I think that that is where a domain expert needs to be involved in the modeling process to identify what the key components and dependencies are. And that's, if I don't know what a tree doctor is, this is not going to elucidate it for me. But in some sense, there should be a handoff where the coder may not need to understand the big picture structure of the model. They may just need to know, I need to write a function called tree doctor that does something, and we'll find out what it does later. And does that make sense?
I think this is also, to your earlier point about coding to the interface, a question of modularization. So just modularizing it starts with distinguishing it and then typing it. So per your earlier slide, like there's a version of these where we would lay in like what are the types that it's observing and what are the types it's writing to, or what can it observe and what can it control. And then you get into more details about like the specifics of why or what it's trying to accomplish or what business logic it employs. And your point now about the domain, that's where the domain information really starts to take over. But in some ways, modularizing it like this would allow some other people to literally not care. Maybe not the person who manages the whole system, like the systems engineer for the whole system needs to have a sense of what all of these things are. But insofar as we're breaking up work and giving different people different chunks of both modeling work as well as implementation work, it might be realistic for someone to kind of focus in on, hey, like, what is the purpose of the tree doctor and how does it, what does it observe and what does it mean for it to make sense of what it observes, what kind of actions it's taking and why becomes a subproblem or a subsystem. And I think, yeah, just the diagram itself serves as an opportunity for modularization that can really unlock progress in a less blocky way.
I've experienced everything in this diagram. Me. Okay.
Okay.
I've been in a scenario where the tree doctor comes, right? You don't know the purpose until you observe. You observe that tree doctor acting over time in a variety of ways. You have to actually be around the tree doctor to know that.
Oh, well,
Okay.
let me tie that back
There's
to
a person
the
I know
roboticsy
that does
machine
this.
learning stuff for a second, Joshua. Because I mean, basically, let's say instead of designing a system, we're observing a system, and we've used a MAID or a cadCAD model as a system representation, and we see an actor acting, but we don't necessarily know what it is, why it's doing what it's doing, or whatever. You can think of that as a black box decision maker. And if you observe its behavior in enough differentiated circumstances and you have a model of its inputs and outputs, you can actually start to do something like a system identification, trying to learn what its behavioral rule is. Now, that will be limited to the scope of circumstances that you've observed it in. So up to some additional modeling, you won't necessarily know how it will behave in circumstances not like the ones you've observed it in, but this is the point where we start to bump up against this field of system identification, or this methodology where you're observing systems. You have some models of them, but they're not totally known, and you're combining those models with data to form beliefs about the rules that are being employed.
Okay. All right. Like,
I will say I've experience with none of this. I've never poisoned a tree, called a tree doctor, built a patio.
I met a person who, like, there's a guy I know, right, who's homeless. Okay. I've seen him let people into their house. You go there and you say, who's that? Right? Right? Good guy. If you don't know this guy, you wouldn't know that. So from the outside looking in, you know, when a homeless person says, "Hey, I don't want any food," they're less hungry than you, and you're confused. Yeah. If they don't buy, if they don't buy food and they purchase labor, right? You have to be around them to know that.
Hey,
Yeah,
Jeff, can
I
we
think
can
each,
we're really close to out of time, and I'd really like Octopus to be able to finish his slides.
sure, it's a great discussion because each agent has their own local model and their own local information that is something the modeler has to consider. I do think that this structuring as a MAID can offer insight into how to set up the cadCAD model initially so that you know what needs to be filled in. And then the question is how to fill it in. So if we look at the dependencies, you can start with level 0. This is a natural thing that happens in graph theory, where anything that does not have any incoming arrows goes on the 0th level. And then you inductively define the next level as anything that has a information or direct cause arrow coming in from the previous level. So here, this lays out the order in which things need to happen based on our model of, for instance, we don't make the decision about whether to call the tree doctor depending until we see whether the tree is sick or not. And this, I think, also goes into the process of building the actual simulation models because it can highlight where these levels, I believe, naturally correspond to the partial state update blocks in a lot of instances. And even if they don't always, this might be a useful heuristic for getting the process started. So at each, here I've partitioned so that the partial state update blocks in the overall structure correspond to the levels as suggested by the graph. And this gives you a model to start with, at least, even if it's whether or not it's ultimately the model that ends up being used. Once you have the graph, again, a non-coder who is competent could translate from the graph to this overall structure. And then the coders come in to begin adding more logic or more structure in different places. But already this gives us a sense of the work that needs to be done, which can be very useful in an organizational process type level.
Yeah, and I mean that's sufficiently boilerplatey that I think part of what I was gesturing at earlier is up to some development, we may get to a place where drawings can literally be translated into boilerplate like this. We don't have that tooling now, but I think it might be low-hanging fruit, assuming that we find this helpful as a team.
And I'd like to put in a plug for process because often people, I mean, modeling is extremely important in creativity, but I do believe that the modeling process can be taught in a structured way that eliminates some of the guesswork. One of my pieces of evidence for this is that the North Carolina School of Science and Math, which is a high school for gifted students in science and math, but still a high school, routinely has their teams place in the top 20 in the COMAP Industrial Mathematics Industrial Congress on Mathematical Modeling competition. And they're outplacing teams that are from elite universities. And it's just because they're a team and they are taught a specific way of modeling in a consistent way, like a sports team might be. And it's evidence that this can be taught and that doing it in a specific way can offer leverage into producing the final outcome in a reasonable way. For context, there are usually tens of thousands of entries. So top 20 is a major result, especially for a high school team to be achieving. So this is wrapping up. We're wrapping up at exactly time. So these are useful frameworks for modeling that are highly compatible and that I believe would make a great start for a way of translating from models to the cadCAD simulations and code. And in the future sessions, based on both our async discussion and things I've already identified in the literature, let's explore this interplay further to tell us what the analytics can do on like the formal mathematical representations and what might be useful at the organizational level of process, where we actually have to communicate and hand work off to each other on a day-to-day basis. All right, thank you so much for everyone who helped me prepare, and I'm happy to address any additional questions or discussion, but I realize we're quite tight on time, so I leave that to the facilitator to determine how to proceed. Thank you very much.
Thank you so much for preparing the material. I think that was incredibly helpful. I think we might as well use the last 5 minutes for any follow-up questions, comments, inputs from team members, maybe with an emphasis on folks who haven't chimed in yet.
Sounds good.
Thank you. I really enjoyed this.
Thank you.
Yeah, this was super helpful. I haven't had a deep dive into MAIDs. I've heard the term a lot. I've had it, described a couple of times, but this was really the first sort of deep dive. So this has been really helpful. Also, the ways that these things were laid out. I really like some of I forget the type of diagrams we're talking about, but laying out utilities and action spaces and the directed graphs between those. I think it's an amazing paradigm. I'm excited to kind of use this for more, simple cases to expand this out. And I'm really curious, where Canvas fits in as far as an interface between this type of thinking and the modeling that goes in behind it. So yeah, really great presentation. Love to hear more about it in the future.
Thank you. I appreciate that.
So Lego had a toy
Mhm.
where you put together these like puzzle pieces as programming, you build it, and it does stuff. Imagine that multiple, right? In that scenario, I'm the one with agency. But I know that. Okay? If I tell somebody, hey, I'm the one that programmed this toy, okay, with these puzzle pieces, right? I could just tell them that. They don't necessarily know why I programmed it that way. They could see it do things and speculate as to why it's happened. So the why comes from me. Okay? If I program it to interact with a pet, which I did, right? The experience that pet, I had a cat named Sauvage. I used to play with I programmed this thing to play with Sauvage. Okay? Sauvage may not know that the way Sauvage interprets what I did might be different to what my intentions were. These are the things that I'm worried about. So
I don't know that you need to worry. I think, Joshua, big part of the modeling that we're doing is figuring out how and when to bring things like, where agency over decisions resides into focus. A lot of modeling techniques kind of obscure away the distributed nature of the decision-making authority by doing things like choosing models of behavior that are quote unquote optimal, or just like generally imposing them rather than viewing them as, I think Octopus mentioned earlier, potentially as parameters, where we are saying, hey, we don't have control of this actor group. We know what their space of admissible actions are, what they're allowed to do. We know maybe something about what they can observe and what they can't observe. We know what potentially the consequences of their decisions might be, up to some state transition rules predicated on their admissible actions, but we really don't know, and we probably shouldn't assume that we know their decision rule. And just the ability to move into a modeling framework or collection of modeling frameworks that allow us to be explicit about when we don't know why or what decision someone's going to make, and then look at our overall, say, mechanism or market designs with the questions about the potential consequences or sensitivities to those uncertainties, is already a pretty big step forward. So less a worry, it's more of a, hey, we're opening this up to analysis.
Okay, I understand. as long as one can participate in the analysis itself, it reduces the fear a little. They could just participate in it. Okay. The action space can be known. Okay.
I'm going to make one last comment with regards to something RJ said about board games. I actually use board game analogies when I'm thinking about designing systems as well, although not necessarily designing board games. I have not designed board games, but I used to play a lot of board games. And the heuristic that I forget where I learned it is that the physical pieces on the board gives you a sense of like the state maintenance, and that the rules enforcement, the cognitive load of enforcing rules in a board game, because obviously you just got players reading the book, you don't have automations, gives you a sense of the kind of rule complexity or whether you've overdone it. So if you're trying to regularize or limit complexity without oversimplifying, the board game analogy for these, especially these multi-stage repeated game type models, it's actually really strong. If it starts to feel like you're maintaining too much state, you could imagine what it would look like to try to encode it in physical pieces on a board. Like what would the board have to look like and what pieces would be required? And if you're thinking about the complexity of the rules, that maps to like how much cognitive load would be placed on the players of the game. Anyway, just like useful heuristics for mapping to that subproblem. Or not subproblem, but related problem.
Understood.
I guess any final closing comments from Octopus, and then we should break so that people can get on with their day.
Yeah, so my final comment would be I'm happy there's a channel for this in the Slack, and I would be happy to continue discussion async. I do have a rough outline of the remaining 3 sessions, so I can't do like a complete refactor. But certainly if people have specific questions or comments that might be possible to incorporate them, I'm always open to feedback within the realm of pragmatism. And I really appreciate everyone coming. The story is told of J.J. Sylvester and is told of many mathematicians who was writing on a whiteboard and no students had come that day. And his colleague said, "Professor, what are you doing?" And he said, "I'm presenting important information." And his colleague said, "But no one is here." And he said, "What difference does that make?" I think having multiple well-informed people to share this as a discussion rather than just a presentation, I enjoy it so much more. So I really appreciate all of you coming and adding your thoughts and ideas.
Well, thank you so much, and we will see you next time, and we'll see you in the chat and in the Slack channel, that is. And I'm just excited for us to continue to refine, improve, and document these methodologies since we kind of use them week in, week out.
Awesome. Thanks all. Catch you again
That was
soon.
great,
See
Octopus.
you in the MAIDs
Thanks.
channel.
Thanks
See
all.
you guys. Bye.